You know, it really feels like we're living in an age of digital magic. AI can now take a single static photograph and just breathe life into it. It can transform a still image into a moving video. It's the kind of stuff that, not too long ago, was pure science fiction.
I mean, just look at this. This incredible image of a shark. It's not just a cool picture, it's the actual starting point for a video where this thing swims right through the water. This is the awesome power of modern image-to-video AI. But behind this amazing trick, there's a huge challenge.
Yep, all this magic comes at a price. And I'm not just talking about money. I'm talking about time, processing power, and just massive computational resources. So what is really going on under the hood that makes this so difficult? You've probably seen AI images exploding everywhere, right? But video has been lagging behind. And why is that? Well, it's because video is just so much harder. You're dealing with way more complex architecture, not as much good training data, and the computational demands are just staggering. To put it really simply, generating video is one of the absolute heaviest lifts in the entire field of AI. This makes finding efficiencies and shortcuts not just a nice little bonus, but an absolutely critical step if this technology is ever going to truly take off.
So a team of researchers decided to pop the hood on a really popular model called Stable Video Diffusion. You've probably heard of it as SVD. They had this hunch, this suspicion that there might be a flaw, a serious inefficiency hiding in plain sight deep inside its code. Let's dig into what they found.
Okay, first, we gotta understand a key component called cross-attention. The best way to think of it is like a film director. Its whole job is to look at that first image and constantly tell the AI, okay, pay attention to this part. Keep this detail looking the same. This is what's important here. It's the guidance system.
All right, so if cross-attention is our director, what's the script that it's reading from? Well, that's something called the clip image embedding. Clip is absolutely brilliant at looking at an image and just boiling it down to its core essence, a bunch of numbers that basically act as a description of what's in the picture. And this is where we get to the heart of the problem. See, Clip was designed and trained to understand single, static images. But video's all about motion, about change, and about how things look from one second to the next. That's the temporal dimension. The researchers started to think, wait a minute, we're using a fantastic tool, but for completely the wrong job.
So, how do you prove a theory like that? You design a really clever experiment. The researchers set up a test to see if Clip was actually understanding the motion in a video or if it was just looking at all the frames like they were a bunch of separate photographs.
First up, they took a video with a ton of motion. You can see here, between the very first frame and the last frame, pretty much everything has changed. The ship's angle, the camera's viewpoint, even stuff in the background. There is a lot of change happening over time.
Next, for comparison, they took a video with almost no motion at all. A seagull, just standing there. As you can see, the first and last frames are pretty much identical. So we've got one video with high motion and one with basically zero motion.
Now here's the kicker. The researchers asked Clip to compare the start and end frames for both videos. And unbelievably, Clip gave them almost the exact same, very high similarity score. It was essentially blind all the chaos and motion in the ship video. It couldn't tell the difference.
This experiment basically sealed the deal. It proved their hunch was right. As the paper puts it, clip embeddings just aren't built to understand temporal features, the very thing that makes a video a video. Our director was reading from a script that was missing all the instructions about movement.
So this discovery led them to a really beautiful, elegant solution they call VCUT. And you want to know the best part? It's training free. They didn't have to spend weeks and a ton of money retraining this massive AI model from scratch. They found a way to just perform a little bit of clever, precise surgery.
So how's it work? Well, it's kind of brilliant. First, they just ripped out the part of the cross-attention that was trying and failing to understand time. It was just getting in the way. Second, they swapped out another complex part for a much simpler, more efficient layer. And third, they split the whole video making process into two stages, an early one to get the main idea right, and a later one just to polish it up and make it look good. Simple and smart.
Okay, so the theory is sound, but did it actually work in practice? Well, the results are pretty staggering. By just cutting out the inefficient parts, they didn't just keep the same quality, they actually improved things across the board.
Let's talk speed. The VCUT method cut latency by about 20%. Now, that might not sound like a crazy number, but in this world, that is a huge leap in efficiency. It means for every 5 videos the old model could make, the new one can pump out 6.
And the model itself got a lot leaner. They were able to remove 50 million parameters just by swapping out that one complex part. This made the whole model lighter and much more efficient without losing any of its power.
But what about the videos? How do they look? Let's go back to our shark. On the left, you've got the original. On the right, the VCUT model. By getting rid of that flawed guidance system, the model was actually freed up to create more dynamic, more interesting motion. It just feels more alive.
And here's something really surprising. You might think that removing a part would hurt how consistent the video is, but in some cases, it actually made it better. Just look at this teapot. The VCUT model on the right does a much better job of keeping the little details on the object consistent as it moves.
And finally, just the overall quality. The VCUT model doesn't just keep up, it can actually make things sharper and less blurry. On the right, that butterfly's wings are way clearer and more defined. So you're getting more speed and better quality. It's a total win-win. So the really big takeaway here is fascinating. We all tend to think that the only way forward for AI is just to build bigger, and even bigger models. But this research shows that sometimes the biggest breakthroughs come from just looking closer at what we already have and finding smarter, more elegant ways to make them work.
And that leaves us with this one last pretty provocative question. It really makes you wonder, what other huge inefficiencies are just hiding in plain sight? Maybe the next great leap forward in AI isn't something we need to invent from scratch, but something we just need to discover, already hidden deep inside the models we use every day.